Hello everyone, welcome back to another MCR3U1 tutoring video. Today we are continuing Chapter 2, Equivalent Algebraic Expressions, and the topic we will cover in this video will be adding and subtracting polynomials. Here we can see the chapter outline once again. The textbook section for today's topic will be 2.1, and you can find some extra practice questions, which of course I recommend you go ahead and do after the video, on pages 88 to 90. So let's get started. Okay, so here's the success criteria for this lesson. Overall, we are trying to reinforce our understanding of polynomials. But more specifically, we want to learn how to add and subtract polynomials. Then we want to learn how to test two polynomials for equivalence. And finally, we want to understand why two polynomial functions are equivalent or not, graphically and algebraically. So first, let's go over the simple steps we need to take to add and subtract polynomials together. Firstly, if there are any brackets in the question, we want to go ahead and get rid of them, like here, 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 and here. And there's a simple rule for taking out the brackets and knowing what sign to use on each term. If the sign before the bracket is positive, and here it would also just be a positive sign, we want to keep all the signs the same on each term. So you can see here that the 9 is positive here, the 9 stays positive here, the 50 is negative here, and the 50 stays negative here, and the 12 is positive here, and the 12 stays positive here. If we move on to the next example, we have a negative sign. So if there's a negative sign before the brackets, the sign's going to change for each term. So we have a positive 9 here and a negative 9 here. We have a negative 50 here and a positive 50 here. And we have a positive 12 here and a negative 12 here. Okay? The way I like to think about it is that there's a positive 1 right here or a negative 1 before the brackets. And all you're doing is multiplying that positive or negative 1 into each term in the brackets using the distributive property. Once we get rid of the brackets, we simply want to collect like terms, meaning we want to look for the terms that have the same variables raised to the same exponents, and we want to add or subtract their coefficients. So here we can see that this 17 has an x squared, and this 12 also has an x squared. So we want to go ahead and add the 17 and the 12, which will get us 29. And that's what we write down here. And we want to do that for all the terms. We have a 4x and a negative 50. So we want to do 4 minus 50. We get negative 46. And then negative 11 plus 9, we get a negative 2. And in this example over here, which is this example up top, we want to do the same thing. The signs just changed now. So we want to do 17x squared minus 12x squared, which will get us 5x squared, and then 4x plus 50x, which will get us 54x, and then negative 11 minus 9, which will get us negative 20. Okay, so now let's move on and do some examples using these two steps that we just learned. So the first example, it says simplify the expression bracket x squared minus 6x plus 1 bracket minus bracket negative x squared minus 6x plus 5 bracket. So as I said before, step 1 is to get rid of the brackets. In the first set of brackets, we have a positive before the brackets, so we just want to keep all the signs the same. So here we go. We do equals x squared minus 6x plus 1. And in the second example, we have a negative before the brackets. So we want to go ahead and pretend there's a negative 1 here and multiply it to each term inside the brackets. So negative 1 times negative x squared, positive x squared, negative 1 times negative 6x, positive 6x, negative 1 times positive 5, negative 5. And now all we want to do is collect like terms, right? So we have an x here raised to the exponent 2. We have another x here raised to the exponent 2, right? So all we want to do is add the coefficients, which are 1 and 1. 1 plus 1 equals 2. X squared, of course. Now we have a 6x here and a 6x here, right? So negative 6x plus 6x will just get us 0. So we don't have to write anything there. And now this positive 1 with no variables, negative 5 with no variables, positive 1 minus 5 will get us negative 4. That's your answer. So here we go on to question 2. We have negative 4x squared minus 2xy, all in brackets, plus 6x squared minus 3xy, plus 2y squared, all in brackets. So again, we want to go ahead and get rid of those brackets. The first one, there's a positive before it, so we just want to keep everything the same, right? Multiply everything by positive 1. And then in the second set of brackets, again, there's a positive sign, so we keep all the signs the same. X squared minus 3xy plus 2y squared. Now we want to collect like terms. So we see that we have an x raised to the power of 2 and an x raised to the power of 2, right? So we're going to add those up. Negative 4, right? Where's the other one? Positive 6, right? Negative 4 plus 6 will give us 2x squared. Next, we have the 2xy and 3xy. Again, let's collect the like terms. Negative 2 minus 3 was negative 5xy. And finally, we have one lone y squared. So we just want to keep that the same, 2y squared. That's our answer. Okay, so on to question 3. We have 3 over 4x plus 1 over 2y, all in brackets, minus 2 over 3x plus 1 over 4y minus 1, all in brackets. So first, we just want to get rid of those brackets. So we have 3 over 4x plus 1 over 2y. Again, positive in front of the brackets. We keep everything the same. Now we have a minus, so we have to switch every sign inside the brackets. So this positive 2 over 3x becomes negative 2 over 3x, right? Positive 1 over 4y becomes negative 1 over 4y. And negative 1 becomes positive 1. Okay, now let's collect our like terms. We have 3 over 4x and 2 over 3x, right? So now we just want to add these rational numbers. So if we take them to the side here to do a quick addition of rational numbers, right? 3 over 4 minus 2 over 3. We want to find the lowest common denominator, which if you multiply the two, 4 times 3, you get 12. So we want to make this denominator 12. But everything we do to the bottom, we have to do to the top. So if we multiply 4 by 3 to get 12, we also have to multiply this 3 by 3. So we do 4 times 3, 3 times 3, right? And then here, we got to multiply this 3 by 4 to get 12. Everything we do to the bottom, we do to the top. So if we do times 4 here, we do times 4 here to keep the number the same. If you multiply the numerator and the denominator by the same number, the number stays the same. So 3 times 3, we get 9, over 4 times 3, we get 12, minus 2 times 4, we get 8, over 12. Now if we subtract these, we'll get 9 minus 8, 1 over 12, right? So back to the question. We have 3 over 4x minus 2 over 3x. We get 1 over 12x, right? Let me erase all this. So we're done with the x's. Let's do the y's. Now we have 1 over 2y and 1 over 4y. So again, we want to make the denominators the same, right? So the lowest common denominator is 4 here. So we just got to multiply this by 2. So of course, whatever we do to the denominator, we do to the numerator. So now we have 2 over 4 minus 1 over 4. And this just ends up being 1/4. Now here we can just put 1/4 y. And finally we just have a 1 here with no variables. So we do plus 1. And that's pretty much the question. There's your answer. Okay, let's move on to the next set of examples. We have here number 4. It says simplify negative bracket 4m squared bracket m minus 2 bracket minus 3m squared plus 5m. So what we want to do here, again, first we want to get rid of the brackets. So we have these set of brackets right here. We have these set of brackets right here. And we always want to get rid of the inside brackets first and then the outside brackets, right? We want to go from the inside to the outside. So to get rid of the inside brackets, we just want to multiply this negative 4m squared by each term inside the brackets using the distributive property. So 4m squared times m will get us 4m cubed, because as we know, when we multiply the same variable, right, we just add the exponents. So here we have m to the power of 2, here we have m to the power of 1, right? And when we multiply them together, we just add the exponents, and we get m cubed in this case, right? Okay, let's continue. Now we have 4m squared times negative 2. That's going to give us negative 8 when we multiply coefficients, and then times m squared, as we had before. And then the rest of the question is negative 3m squared plus 5m. Now we want to get rid of these brackets, which were the outside brackets before. And we do that by multiplying this negative 1, right? If there's a negative in front of the brackets, that means there's kind of a negative 1 here that multiplies each term inside the brackets, again using distributive property. So negative 1 times 4m cubed. We're just going to switch the sign from positive here to negative, right? 4m cubed. And here we have a negative sign, so we're going to switch that to positive. 8m squared, and then everything else is the same. Now that we've gotten rid of all the brackets, we want to collect like terms. So we only have 1m cubed. We're going to keep that the same. Then we have 2m squareds, right? So we're just going to add these coefficients together. In this case, subtract them. We're going to do positive 8 minus 3, which is going to give us positive 5 and then m squared. And then we have 1m here. We're going to keep that the same. And that's our final answer. Okay, moving on to question number 5. This is a word problem, so let's read it. The two equal sides of an isosceles triangle each has, supposed to say has, a length of 2x plus 3y minus 1. And as we know, an isosceles triangle, if we draw it out, oh, that's a bad drawing, has two equal sides, and this side is different, right? And it says each equal side of the isosceles triangle has this length, a length of 2x plus 3y minus 1, and this one's the same, 2x plus 3y minus 1 units, right? Doesn't actually specify in this question. It's just units. Same with this one, units. Okay, let's read the rest of the question. The perimeter of the triangle is 7x plus 9y. Determine the length of the third side. So we have the perimeter, which equals 7x plus 9y. And we have to find the length of this side, which we'll call S. Okay, so how do we do this? Well, we need to find ourselves two equations, right? And using those equations, we can substitute and find the length of the third side, right? So we have this first equation, right, which is the length of the perimeter. But what's also the perimeter of the isosceles triangle? Well, is side 1 plus side 2 plus side 3, right? And side 1, we'll call this side 3 actually, right? This is what we're trying to find, side 3. This is side 1, this is side 2. So it's going to be the perimeter equals side 1 plus side 2 plus side 3. But what do we already know? We know side 1, which is 2x plus 3y minus 1. And we also know S2, side 2, which is the same thing. But we also know the perimeter, which is this, 7x plus 9y, right? So if we substitute all that in, right, we get 7x plus 9y on the left side, right? We're multiplying this p into this p equals side 1 over here, which is 2x plus 3y minus 1. Then we have side 2, which is the exact same thing, plus 2x plus 3y minus 1. Oh. And then we have side 3, which is kind of what we need to look for. So now, let me put brackets around this too. To find side 3, we have to isolate for side 3. So what we don't want to do, right, is subtract each side, right, from this side by negative 2x plus 3y minus 1. We want to do that twice, right? Because we have a 2x plus 3y minus 1 and a 2x plus 3y minus 1. And we want to get rid of these, this whole polynomial, right? And we kind of want to bring it to this side, right? So if we subtract 2x plus 3y minus 1 from both sides, the equation will stay the same, the expression will stay the same, right? But we will have isolated for S3, which is what we don't want to do. So I'm going to give myself a little more space here. I'm going to put the equal sign here, or here, actually. So we have S3 still on this side. And now we're going to have 7x plus 9y minus 2x plus 3y minus 1. Right? Because if we subtract, right, from this side, 2x plus 3y minus 1, we get rid of this term. If we subtract by that again, we get rid of this term. And then we kind of bring it over to this side. And so we get 2 negatives 2x plus 3y minus 1. And that's why there's kind of a 2 here. Just giving us two terms. Two polynomials, actually. So now, we want to get rid of the brackets. So here, we have a positive in front of the brackets. So we just want to say 7x plus 9y. And here on the right side, we're going to do the distributive property. So negative 2 times 2x will give us negative 4x. Negative 2 times positive 3y will give us negative 6y. Negative 2 times negative 1 will give us positive 2. The right side is S3. And now we want to collect like terms. So we have 2x's here, right? 7x minus 4x will give us 3x. Just subtracting the coefficients. Then 9y, negative 6y. We have 9y minus 6y will get us positive 3y. And we just have a 2 here. So plus 2. And that is the length of S3. And it's given in the two variables that the other lengths are given in x and y. So that should be our final answer. If it asks you for the numerical value of the length of the third side, then you'd have, in the question, you'd have your declarations for x and y, and then you would plug them in here and get your numerical value. But in this case, we just leave it as it is. Now let's move on and look at testing for equivalence between two polynomials by seeing what makes two polynomials equivalent and what does not. First, let's go over what makes two polynomials equivalent. So right here. Oh, right here. So the first criteria for two polynomials to be equivalent is that they both must simplify to the same function or expression. So, for example, if we have an f of x here, which could equal 2x plus 2, for example. And we have a g of x, which equals 1 over 2, 4x plus 4. Right? If we simplify g of x by using the distributive property and multiplying the half by every term inside the brackets, right? We would get 2x, right? Half times 4x, 2x. And then half times positive 4 will give us 2, which equals f of x. And now we can say that g of x and f of x are equivalent, right? Because once you simplify g of x, it equals f of x. So let's look at after I erase this, hold on. Now let's look at the second criteria for two polynomial functions or expressions to be equivalent, and that is that both polynomials, functions, right, if you turn them into functions, they both must produce the same graph. Meaning, if we were to graph the two, maybe we start graphing f of x and it looks like this, right? G of x must also look like this, so it'll kind of be over top of of f of x, right? Because for two polynomial functions to be equivalent, for any x value, right, along the x-axis, whatever x value we choose, both f of x and g of x must correspond to the same y value up here, right? So any x value we choose, for example, if we choose 4, f at 4, right, this is the y value of the f function when x equals 4, must equal g at 4. And if whatever number we choose here, it has to equal the same number here. That's how two polynomial functions are equivalent, or expressions. So now let's see what makes two polynomial functions or expressions not equivalent, because this could help us solve a lot of questions. Because if you find one of these criteria, right, in a question that you're asked to test equivalence for two polynomials, we can automatically finish the question right there and say they're not equivalent. Okay, so let's look at these. So first, let's look at this number 2. We'll do this one last. Firstly, if the two functions evaluate to different values when the same variable numbers are substituted in, then the functions are not equivalent. So, as I showed you up here, if you have f of x and you plug in x equals, let's say 5, if that does not equal g of 5, right, they are not equivalent, because for any x value we choose, they have to correspond to the same y value. So if we find this out for any number we choose to put in here, right, if we were doing a question testing for equivalence, we would plug in a few different values for x, and if we find that this is true for one of them, then we can say that the two polynomials are not equivalent. Okay? Now let's move on to number 3 here, right? If the graphs have finite solutions or no solutions at all, meaning a solution is when the graphs touch. So if we have a graph and f of x is like this, and g of x is something like this, some wacky like that, these are the solutions. The solutions is the number of times they touch, right? So if the two graphs of the functions have finite solutions, they are not equivalent, because for the two polynomial functions to be equivalent, they must be like up here, over top of one another, so that for any x value corresponds to the same y value for both functions, right? They must graph the same exact graph. And finally, if we test these two and we can't really say that they're not equivalent from these two tests, we go to number 1 here, and we go to these two criteria up here, and we see by simplifying if they simplify to the same expression, or we just graph them and see if they produce the same graph, right? And that's pretty much it. Okay, so let's move on and do a couple of examples now. It says here, are the following polynomials equivalent? So let's look at number 1. We have f of x, which equals 2x squared plus 7x minus 2, all in brackets, minus 3x plus 7, all in brackets. And we have g of x, which is x squared plus 12, all in brackets, plus x squared plus 4x minus 17, all in brackets. Now, we use the test criteria that we saw on the last slide, and we could go ahead and graph these, see if they produce the same graphs, but because, that will take a lot of time sometimes when you're working with polynomials, we'll just simplify, or we'll sub in numbers as x values, to test if they'll get the same y value. But for this example, or for these couple of examples, I'll just simplify So we get a little more practice with adding and subtracting polynomials and all that stuff. So let's simplify f of x first, right? First, let's get rid of the brackets. There's a positive here, so all the signs are going to stay the same, right? So we just take out the brackets. Everything stays the same. Here we have a negative in front of the brackets, right? In front of this. So we are going to change the signs to the opposite sign. So we have a positive 3x, we make it a negative 3x. Positive 7, we make it a negative 7. Okay, now we collect like terms like we've done before. There's only 1x squared here, so keep that. There's 2 x's, 7 minus 3 will give us 4x, and negative 2 minus 7 will give us negative 9. Now let's simplify g of x. So we'll get rid of these brackets first. There's a positive in front of the bracket, everything stays the same. There's another positive here, everything stays the same here as well. Minus 17, right? Now if we collect like terms, we add the x squareds, which will get us 2x squared. We add the x's, there's only 1x, so we'll keep that, 4x. And we have a 12 minus 17, which will get us negative 5. Now we compare and see if they produce the same polynomial. The coefficient in front of the x squared is the same, okay? So check that off. The coefficients in front of the x's are the same. So far, so good. But now, when we get to the lone coefficients at the end, these do not equal, and therefore f of x will not be equivalent to g of x, right? Because they don't simplify to the same polynomial. And you could even further test this by subbing in a value. For example, f of 1. If you sub in f of 1, you'll get here a 2. You get here a 4 minus 9, which will give you 6 minus 9 give you negative 3, right? And if you sub in a 1 for the g function, you'll get a 2 here, a 4, negative 5, which will give you 6 minus 5, which will give you 1. And now we see that since f of 1 does not equal g of 1, we can say that the two functions are not equivalent because we found an x value which produces two different y values for each function, right? Okay, so let's move on to question 2. Same thing here. We'll simplify these two expressions and we'll see if we get the same expression. So let's simplify f of n here. We have half n squared. We'll keep that. First, we're obviously going to take out the brackets, so let's keep everything else the same for now. Minus 3. Now, we have a positive in front of the brackets, so all the signs are going to stay the same. 1.5 n squared minus 6. We've gotten rid of all the brackets, so now let's collect like terms. We have a 0.5 n squared here, plus 1.5 n squared will get us 2n squared. We have 2n. There's no other n's, so we'll keep that the same. Negative 3 minus 6 will get us negative 9, right? That's f of n. Let's do g of n. Again, let's get rid of the brackets first. So n squared minus n plus 1, we'll keep that the same. Now we have a negative in front of the bracket, so we're kind of multiplying a negative 1 into each term, right? So we're going to switch the signs. Negative n squared turns to positive n squared. Negative 3n turns to positive 3n. Positive 10 turns to negative 10. And if we collect like terms, n squared plus n squared, 2n squared. Negative n plus 3n plus 2n. 1 minus 10 is 9. Negative 9, sorry. So now we can see that for the n squareds, the coefficient is the same. For the n's, the coefficient is the same. And for the lone coefficients, they're also equal. Now we can say that f of n is equivalent to g of n. And again, you can further test this by plugging in some values for n, and you will see that no matter what value, you'll obviously get the same final answer because both expressions simplify to the same polynomial. But if you plug in any n value to these functions up here before simplification, you'll still get the same values. Okay, and let's do one more here. Number 3. Are the expressions xy plus xz plus yz and x squared plus y squared plus z squared equivalent? So here we could we can't really simplify any more than this, so we're going to have to go to the next step, which is plugging in some numbers and seeing if they work, right? We can do a few test cases, and if we find one that doesn't work, then we can say they're not equivalent. And if we see that, we do a few test cases and they're all the same, we might want to graphs to fully make sure if they're totally equivalent, but let's just plug in numbers for now. So we can choose really anything. Let's say x will be 1, y will be 1, and z will be 1. If we plug that into, let's say this is expression 1, this is expression 2. Expression 1 with these variable declarations will be 1 for the x, 1 for the y, plus 1 for the x, 1 for the z, plus 1 for the y, 1 for the z. This will give us 1 plus 1 plus 1, 3. And for E2, expression 2, we will get 1 for the x squared, and 1 squared for the y, and 1 squared for the z. This will give us 1 plus 1 plus 1, which will give us 3. Therefore, when we use these declarations, E1 equals E2. Now, you might be tempted to say, you know what? These equations are now the same. I've tested one number, so you know what? They must be the same. But you cannot fall into that trap, because let's look at what happens if we just switch maybe the x to a 2 and the z to a 2, right? So let's do E1 using these declarations. X is 2 now, y is 1, x is 2, z is 2 now, and then y is still 1, z is 2. So now E1 will be 2 here, plus 4 here, plus 2 here. Expression 1 will evaluate to 8. Now if we do expression 2 here on the side, we can see that x is going to be 2 now, squared, plus y, which is still 1, squared, plus z, which is now 2, squared. This will simplify or evaluate to 4 plus 1 plus 4, which will evaluate to 9. And now we can see that expression 1 does not equal expression 2 when we use these declarations. And so we found a test case of variable numbers, right? We've found that when x equals 2 and y equals 1 and z equals 2, these expressions do not simplify or do not evaluate to the same number. And once we found this, we can say that expression 1 is not equivalent to expression 2, right? Because we found a test case where the first expression does not equal the second expression. And if you wanted to turn these into functions, let's say this is function f in terms of x, y, and z, and this is function g in terms of x, y, and z, right? And if you graph these, it'll be a really, really complicated graphs, but if you graph these at these coordinates, these graphs will not be at the same value. And therefore, if that happens, we can say that the two functions are not equivalent. Not for every value that we choose, they won't evaluate to the same final numerical value. Before we end the lesson, I just want to go over how we can tell if two polynomials are equivalent by graphing them. What it really means for two polynomial functions to be equivalent is that for every single x value, no matter how small or big, so if you keep going down this x-axis, you can get to 1 million, 2 million of an x value, and then if you go this way, -1 million, -2 million, it just keeps on going till infinity, right? No matter how small or big you get, the two functions must produce the same y value, and therefore the graphs will have infinite solutions if this happens. If the polynomials are parallel, like in this example right here, right? These two polynomials will keep on going and going and going and going this way to infinity and this way to infinity, and they will never ever touch. If this happens, they won't even have a single solution, making it impossible for them to be equivalent. Because for two functions to be equivalent, they must touch at every x value, right? So there's no way that a graph with parallel lines will be equivalent. Two graphs with finite solutions, right here, will have various x values that correspond to the same common y value. So we can see here that these two graphs have a common y value. Let's say this is x equals 1, common y value at x equals 0, and common y value at x equals, looks like 3, right? But for the functions will still be non-equivalent because not every x value produces the same y value for each graph. So if we pick right here, this would be like x equals 2, right? If we go up, we'll touch this graph up here, and we'll touch this graph down here. So this one will have like a y value of 1. This one will have like a y value of, I don't know, -3, right? So they don't correspond to the same y value, and we can pick a lot of more x values where this case will happen, where the y values won't match, right? So from this, we can tell that they're not equivalent. And this is actually a -1, sorry about that. So let's move on. Lastly, we have infinite solutions. I know you can't really see the graphs right here, but that's because one line is over top of another. So here's g of x, right? I've graphed it, and f of x will be right over top of it. If this happens, they will have infinite solutions. So for any x value you choose along this x-axis, they will have and correspond to the same y value. So in summary, unless the graphs have an infinite solution, unless the graph have infinite solutions, like here, they are not equivalent. So these two cases, the graphs are not equivalent if they have no solution at all or have only a number of solutions that you can count to. If they have infinite solutions, then they're equivalent. Okay guys, thank you so much for watching, and make sure you keep on practicing because the examples we do in the video are never enough to really test your understanding, and you always want to look at more, example cases and whatnot.